physicists have been captivated by black holes for an extended period, a phenomenon that has intrigued scientists for over 100 years. These enormous entities, which challenge our understanding of gravity, remain mostly invisible to us. A black hole that is 2 to 4 million times heavier than the Sun is tremendously powerful. However, due to decades of research, our knowledge has evolved from nearly nothing to uncovering more details, sometimes in unexpected ways. A recent breakthrough has occurred with researchers, including those who announced at the Kaku Institute, that they've been able to peer inside a black hole. This new data has revealed aspects of the universe that science may have previously missed. Let's delve deeper into black holes and explore the secrets they may hold. Space is vast and awe-inspiring. But before diving into the recent revelations, it's important to understand the fundamentals of black holes. While many people are familiar with the concept of black holes, significant gaps in our comprehension still remain. The theoretical possibility of a black hole emerged in 1916 when Albert Einstein introduced his general theory of relativity, which suggested such objects could exist. Nevertheless, black holes remained speculative until the 1960s, when scientists made their first observations solid evidence that pointed to their existence. While studying the binary star system, Cygnus X1, astronomers discovered an unusually bright blue star emitting X-rays. This star was not a typical celestial body. It was orbiting a mysterious massive object. Upon further investigation, it became evident that the X-rays weren't just floating in space, or being drawn toward this dark entity, confirming the presence of a black hole. This was a significant discovery, a milestone proving that black holes were not just theoretical ideas but tangible phenomena. The importance of this finding cannot be overstated, as it meant that an entirely new category of objects existed in space, demanding urgent and careful study. Researchers worldwide then focused their attention on black holes with renewed interest. The first confirmed black hole, Cygnus X1, is located around 6,000 light-years from Earth in the Cygnus constellation. It is much brighter than our Sun and has an enormous gravitational pull so intense that even light cannot escape it. This is why it is referred to as a black hole. The nature of a black hole is both fascinating and daunting. It denotes a region in space where the gravitational force is so powerful that nothing, no matter or light, can break free from its pull. Anything that is too close to a black hole is inevitably sucked in and lost forever. This threat makes studying black holes both important and compelling, but does this mean we're in immediate danger from them? Despite the nearest black hole being about 500 light-years away, this distance still raises concerns about potential risks. However, the true scale of black holes is only just beginning to be understood. Following the discovery of Cygnus, 10-1, astronomers began searching for more black holes. It's currently believed that there may be up to 100 million black holes in the Milky Way galaxy alone. Good. Though identifying them remains a difficult task. Estimates suggest that millions exist within our galaxy, highlighting the significance of examining these mysterious objects. The primary concern with black holes is their immense gravitational force. This pull is so strong that it draws in everything, including light. The core of the black hole, known as the singularity, is where all the matter that falls into it is compacted into an infinitely dense point. In simpler terms, black holes act as cosmic vacuum cleaners, pulling in everything within their reach. If a person were to fall into a black hole, they would be stretched and compressed until they were reduced to the singularity. This process is incredibly slow, meaning the individual would die long before reaching the final, irreversible stage. Yet, despite the apparent danger, black holes are so widespread that they cannot be disregarded. Even though the closest one is far away, the sheer number of them in our galaxy makes them a critical subject for scientific study. In 2019, scientists reached a historic achievement by capturing the first clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. This photograph was taken over a number of nights, and for each exposure, more insights were gathered. The data was painstakingly compiled to create a clearer image. The most remarkable finding was that a black hole isn't merely a singular void. In space, it consists of three distinct layers. The first layer is called the event horizon, marking the point beyond which nothing can return. Once an object crosses this boundary, it is inevitably drawn toward the black hole. The second layer is known as the photon sphere, where light is trapped in orbit. Any light that enters this region is caught in the black hole's gravitational grasp and cannot escape. Lastly, the third layer is the singularity, where matter is compressed into a single point in spacetime, creating a region where the laws of physics, as we know them, no longer apply. This breakdown of the laws of physics is one of the many reasons that studying black holes is so challenging and captivating. What's even more fascinating is that each black hole behaves differently. While they share a similar basic structure, each one operates in its own unique way. Unlike other celestial objects that we can study directly, black holes can only be examined indirectly. Scientists rely on observing the radiation emitted by black holes and the surrounding gas and dust. Sending a probe into a black hole is impossible, as anything that crosses the event horizon is pulled into the singularity, where it would break down into an infinitesimally small point. This limitation forces researchers to rely on two-dimensional models to study these three-dimensional objects. Furthermore, black holes come in various shapes and sizes, adding another layer of complexity to their study. Researchers have proposed several theories to explain how black holes develop, with one of the most accepted being that they originate from collapsing stars. When a star runs out of fuel, it can no longer generate the energy needed to counterbalance the force of gravity that causes it to collapse. If the star is sufficiently massive, this collapse continues until the star becomes a singularity. Researchers have focused on a particularly powerful galaxy, M87, where they observed a massive whirlpool of hydrogen gas rotating at an incredible speed of 1.2 million miles per hour. Despite the extreme forces at play, the gas didn't fly apart, leading scientists to deduce that there must be a massive object at the galaxy's center. This object, which keeps everything together, has turned out to be a black hole with a mass billions of times that of the Sun. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to model rotating black holes. Kerr's theory proposed that instead of collapsing into a singular point, a rotating black hole could form a ring of fire or an accretion disk. This disk would rotate so quickly that the outward forces would counterbalance the gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole. A wormhole is a hypothetical tunnel connecting to distant points in space-time, potentially even linking parallel universes. The idea of wormholes has intrigued scientists for years. If black holes are indeed connected to wormholes, they could provide shortcuts via space-time, making travel possible between far-off regions of the universe or even different points in time. However, even if wormholes exist, it's unlikely that we would be able to use them for travel anytime soon. According to Einstein's theory of special relativity, the speed of light is the ultimate limit on how fast anything can travel, creating a barrier for using wormholes for faster-than-light travel. Wormholes remain an exciting area of theoretical research. If stabilized, they could allow for traveling over extensive distances of space, or even to different points in time. Some physicists also propose that wormholes might offer a mechanism for time travel. However, the challenges of traversing a wormhole are enormous, as they would likely be unstable and surrounded by extreme radiation and gravitational forces. To truly understand the nature of black holes, physicists must come up with a single theory that combines both Einstein's general relativity and quantum mechanics. One promising candidate for this theory is superstring theory, which suggests that the fundamental particles of nature are actually tiny, vibrating strings. The strings could explain many of the enigmatic phenomena of the universe, including the formation of black holes and wormholes. Superstring theory also suggests that black holes, wormholes, and other exotic solutions to Einstein's equations can lead to the bending of spacetime caused by these tiny strings. Despite its potential, superstring theory requires the existence of additional dimensions of spacetime that are too minute for us to notice. Nevertheless, Research into black holes and their mysteries continues to push the boundaries of our understanding. The most revolutionary ideas related to black holes is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that black holes aren't completely black, but emit faint radiation due to quantum effects near their event horizons. This radiation could gradually cause the black hole to lose mass, ultimately leading to its evaporation. Although Hawking radiation is difficult to detect due to its weak nature, it provides valuable insights into the behavior of black holes and their role in the universe. Black holes also serve as unique laboratories for studying the interaction between gravity and quantum mechanics. The extreme conditions near a black hole singularity, where both gravitational forces and quantum effects become relevant, making them an essential part of research for physicists seeking to develop a theory of quantum gravity. The study of black holes may also offer clues about the origins of the universe. Some theories suggest that the conditions near a black hole could provide insights into the birth of space-time itself. Additionally, if wormholes do exist, they could present a mechanism for exploring vast regions of space-time, opening up new possibilities for interstellar travel. Although these ideas remain speculative, they continue to inspire researchers to seek answers to the most profound questions about the nature of our universe. Black holes have sparked a profound fascination among researchers. Their study has evolved dramatically over the years. These enigmatic cosmic entities defy many of our standard understandings of physics, particularly gravity. The fact that they are almost invisible makes them even more intriguing, and scientists continue to probe their mysteries with intense curiosity. As our technological and theoretical knowledge improves, our comprehension of black holes becomes deeper and more complex. It's clear that black holes are not just fascinating relics of space, but also serve as crucial pieces of the cosmic puzzle that might help unlock the mysteries of the universe. As we progress in our understanding, black holes remain one of the most complex and fascinating subjects in astrophysics. Their ability to bend and warp space-time itself gives them an extraordinary place in the study of cosmology. As we continue our investigation of their secrets, we inch closer to understanding the fundamental mechanics of the universe, including the very nature of space-time and matter. The study of black holes provides an understanding of the way gravity interacts with quantum forces, opening new avenues of research that could one day provide answers to some of the most fundamental concerns regarding the fabric of the cosmos. One of the most important ongoing challenges for physicists is reconciling the theoretical differences between general relativity, which describes the large-scale gravity behavior, and quantum mechanics, which governs the subatomic world. Black holes, with their extreme conditions, provide a natural laboratory for studying these forces side by side. They are some of the few places in the universe where the effects of both gravity and quantum mechanics become apparent in ways that are difficult to replicate in a terrestrial environment. This duality makes black holes uniquely valuable to researchers who are working to develop a unified theory, physics that can encompass both of these fundamental forces. The attempts to comprehend black holes have led to a number of groundbreaking discoveries, one of the most notable being the detection of gravitational waves. These ripples in space-time, first predicted by Einstein in the early 20th century, are caused by the acceleration of massive objects, such as the collision and merger of black holes. The observation of these waves, first confirmed in 2015, began a new era in astrophysics, allowing researchers to investigate cosmic events that were previously beyond the reach of traditional observation methods. Gravitational wave astronomy has provided us with new perspectives on the universe, offering fresh insights into the behavior of black holes and their role in the cosmos. Despite all the progress made in the study of black holes, there is still much to learn. As technology advances, so too does our ability to see the universe from new and more profound perspectives. The creation of more powerful telescopes, both on Earth and in space, has expanded our ability to observe distant black holes, revealing new details about their structure and behavior. Additionally, the development of advanced computational models and simulations has allowed scientists to model the complex dynamics of black holes and their environments with unprecedented accuracy. These tools will continue to deepen our comprehension of these cosmic giants and their impact on the universe. Looking to the future, the continued study of black holes is expected to yield even more astonishing revelations. As we work to improve observational techniques and push the boundaries of theoretical physics, we may uncover new aspects of black holes that challenge even our most established ideas about the nature of reality. The possibility of discovering new types of black holes, understanding their role in galaxy formation, and exploring the relationship between black holes and the fundamental structure of space-time are just a few of the exciting avenues of research that lie ahead. Moreover, the study of black holes is likely to have far-reaching implications for other fields of science. By understanding the extreme conditions near a black hole's singularity, we may gain insights into the behavior of matter and energy under conditions that are otherwise impossible to replicate. This could have applications not only in astrophysics, but also in fields like material science, quantum computing, and even the development of new technologies. In addition to the practical scientific advancements, the exploration of black holes continues to captivate the worldwide public's imagination. The mystery of what lies beyond the event horizon is the ultimate fate of anything that crosses it, and the strange, often paradoxical nature of these objects continue to amaze people with wonder and curiosity. For many, the concept of black holes evokes images of cosmic adventure, leading to a deeper philosophical inquiry into the nature of existence, time, and the universe itself. As we continue our investigation of black holes, we are reminded that our understanding of the universe is far from complete. These enigmatic objects challenge our most fundamental concepts of physics and offer a window into the deepest aspects of the universe. The path to unlocking their secrets is a long one, but each discovery brings us closer to understanding the fundamental forces that shape the universe. In conclusion, black holes are not merely astronomical oddities, but rather key players in the cosmic dance of the universe. They hold the potential to answer some of the most profound questions about space-time and the nature of reality. While we have made incredible progress in understanding them, black holes remain a fascinating enigma that continues to drive research and fuel the imagination of researchers and non-researchers alike. The ongoing study of these mysterious entities will undoubtedly continue to yield surprising and groundbreaking insights, providing us with a deeper understanding of the universe and our place within it.